Good morning. Okay. Let's get started. We have one handout today. That's your lecture notes. There's some copies still outside for those who haven't picked one up. In general, what I do is that in the lecture notes, I leave out large parts of, large amounts of material. So this will, enable you to keep your hands busy while I'm lecturing and take down some notes and so on. So don't assume that everything that I talk about is on here. Please follow along. Okay. So as is my usual practice, let me start with a quick review of what we covered so far. So what we did primarily was looked at this discipline that we called the lumped matter discipline, which was very similar, very reminiscent of the point mass simplification in physics. And this discipline, this set of constraints we imposed on ourselves, allowed us to move from Maxwell's equations to a very, very simple form of algebraic equations. And specifically, discipline took two forms. One is, we said that we will deal with elements for whom the rate of change of magnetic flux is 0 outside the elements, and for whom the rate of change of charge, amount of charge, inside the element was 0. So if I took any element, any element that I called a lumped circuit element, like a resistor or a voltage source, and I put a black box around it, then what I'm saying is that the net charge inside that is going to be 0. Now, this is not true in general. Okay, we will see examples where if you choose some piece of an element, for example, there might be charge buildup, but net inside the, if I put a box around the entire element, I'm going to assume that the rate of change of charge is going to be 0. So what this did was it enabled us to create the lumped circuit abstraction, where I could take elements, some element of this sort. This could be a resistor, a voltage source, or whatever. And I could now ascribe a voltage, some voltage across the element, and also some current I that was going into the element. And as I go forward, when I label the voltages and currents across and through elements, I'm going to be following a convention. Okay, the convention is that I'm going to label, if I label V in the following manner, then I'm going to label I for that element as the current flowing into the positive terminal. Okay? By doing this, it's just a convention. By doing this, it turns out that the power consumed by the element is VI is positive. Okay? So by choosing I going in this way into the positive terminal, the power consumed by the element is going to be positive. Okay, so in general, we will simply follow this convention. When I label voltages and currents, I'll be labeling the current into an element entering in through the plus terminal. Remember, of course, if the current is going this way, let's have a 1 amp of current flowing this way, then when I compute the current, I will come out to be negative. Okay. So by making these assumptions of the lumped matter discipline, I said I was able to simplify my life tremendously. And in particular, what it did was it allowed me to take Maxwell's equations, okay, and simplify them into a very simple algebraic form, which has both a voltage law and a current law that I call Kirchhoff's voltage law and Kirchhoff's current law. KVL simply states that if I have some circuit, and if I measure the voltages in any loop in the circuit, So if I look at the voltages in any loop, then the voltages in a loop would sum to 0. Okay? So I measure voltages in a loop, and they will sum to 0. Similarly, for the current, if I take a node of a circuit, if I build a circuit, a node is a point in the circuit where multiple edges connect. If I take a node, then the current coming into that node, the net current coming into a node is going to be 0. Okay, so if I take any node of a circuit and sum up all the currents coming into that node, they will all net sum to 0. So notice that what I've done is, by this discipline, by this constraint I imposed on myself, I was able to make this incredible leap from Maxwell's equations to these really, really simple algebraic equations, KVL and KCL. And I promise you, okay, going forward through the rest of 6002, if this is all you know, okay, you can pretty much solve any circuit using these two very simple relations. Okay, it's actually really, really simple. It's all very simple algebra. Okay? So just to show you an example, let me do a little demonstration. Let me build a small circuit and measure some voltages for you and show you that the voltages indeed add up to 0. So here's my little circuit. So I'm going to show you a simple circuit that looks like this, and let's go ahead and measure some voltages and currents. In terms of terminology, remember, this is called a loop. So if I start from the point C, and I travel through the voltage source, come to the node A, down through R1, and all the way down through R2 back to C, that's a loop. Similarly, this point A is a node where the resistor R1, the voltage source V0, and R4 are connected. Okay, just make sure your terminology is correct. So what I'll do is let me make some quick measurements for you and show you that these KVL and KCL are indeed true. So the circuit's up there. Could I have a volunteer? Any volunteer? All you have to do is write things on the board. Come on over. Okay, so let me take some measurements, and why don't you write down what I measure on the board. What I'll do is, let me borrow another piece of chalk here. What I'll do is focus on this loop here, and focus on this node, and make some measurements. All right. So you see the circuit up there? Okay, so I get 3 volts for the voltage from C to A. So I want to write down 3 volts. Okay, so the next one is minus 1.6. And so that will be, I'm doing AB, VAB. Okay, and then let me do the last one, and it is minus 1.37. Actually, the measurements, I guess, I have made have been this way. So it's what's written is VAC, but it's okay for now. Don't worry about it. So, so within, well, thank you. I appreciate your help here. Okay, so within bounds of experimental error, notice that if I add up these three voltages, they nicely sum up to 0. Okay. Next, let me focus on this node here, and at this node, let me go ahead and measure some currents. What I'll do now is change to an AC voltage so that I can go ahead and measure the current without breaking my circuit. Okay, this time around, you'll get to see the measurements that I'm taking as well. So what I have here, I guess you can see it this way. What I have here is 3 wires that I have pulled out from D, and this is the node D, okay? So I have 3 wires coming into the node D just to make it a little bit easier for me to measure stuff. Okay, so everybody keep your fingers crossed so I don't look like a fool here. Hope this works out. Okay, so you roughly get, what's that? 10 millivolts. Okay, so it's about 10 millivolts peak to peak out there. And notice that, let's say that if the waveform rises on the left-hand side, it's positive. So it's positive 10 millivolts. And another positive 10 millivolts, so that's 20 millivolts. And this time it's a negative, roughly 20, I guess. Negative 20. So I'm getting, in terms of currents, I have a negative 10, I'm sorry, a positive 10, a positive 10, and a negative 20 that adds up to 0. But more interestingly, I can show you the same thing by holding this current measuring probe directly across that node, and notice that the net current that is entering into this node here is 0. Okay? So that should just show you that KCL does indeed hold in practice, and it is not just a figment of our imaginations. Okay. So before I go on, I wanted to point one other thing out. Notice that I've written down 2 assumptions of the lumped matter discipline. Okay? There is a third assumption of the lumped matter discipline, and that assumption is, in spirit at least, shared by the point mass simplification in physics as well. Can someone tell me what that assumption is? A third assumption, which I did not mention, which you can read in your notes in section A.2 in the appendix. What's the third assumption that is shared in spirit with the point mass simplification? Anybody? The third assumption we made here is that in all the signals that we're going to study in this course, we made the assumption that the signal speeds of interest, transition speeds and so on, are much slower than the speed of light. Okay? That my signal transition speeds of interest are much slower than the speed of light. Remember, the laws of motion, the discrete laws of motion break down if your objects begin moving at the speed of light. Okay, the same token here, our lumped circuit abstraction breaks down if we approach the speed of light. And there are follow-on courses that talk about waveguides and other distributed analysis techniques that deal with signals that travel at the speed, close to speeds of light. Okay. So with that, let me go on to talking about method 1 of circuit analysis. This is called the basic KVL-KCL method. So just based on those 2 simple algebraic relations, I can analyze very interesting and complicated circuits. The method goes as follows. So let's say our goal is, given a circuit like this, our goal is to solve it. Okay, in this course, we will be doing two kinds of things, analysis and synthesis. Analysis says, given a circuit, okay, what can you tell me about the circuit? Okay, so we'll solve existing circuits for all the voltages and currents, voltages across elements and currents through those elements. Synthesis says, given a function, I may ask you to go and build circuits. Okay, so for analysis here, we can apply this method that I'm about to show you. And the idea here is that, given a circuit like this, let us figure out all the voltages and currents that are a function of the way these elements are connected. So the basic KVL and KCL method has the following steps. The first step is to write down the element VI relationships. Okay, write down the element VI relationships for all the elements. Second step is write KCL for all the nodes. And the third step is to write KVL for all the loops in the circuit. That's it. Just go ahead and write down element rules, KVL and KCL, and then go ahead and solve the circuit. So we'll do an example, of course. But just for your, as a refresher, we've looked at a bunch of elements so far. And for a resistor, the element relation says that V is IR, where R is the resistance of the element here. For a voltage source, V is equal to V naught. That's the element relationship. And for a current source, the relation is I is simply the current flowing through the element. Okay, so these are some of the simple element rules for the devices that the current source, voltage source, and the resistor. So let's go ahead and solve a simple circuit. And what I'll do is go ahead and solve this circuit for you. Okay, if you turn to page 5 of your notes, I'm going to go ahead and edit this circuit here. You can scribble the values on your notes on page 5. Okay, so as the first step of my KVL KCL method, I need to write down all my element VI relationships. So before I do that, let me go ahead and label all the voltages and currents that are unknowns in the circuit. So let me label the voltages and currents associated with the voltage source, I0. Notice I continue to follow this convention where whenever I label voltages and currents for an element, I will show the current going into the positive terminal of the element variable, okay, of the element variable voltage. So so here I have V naught and I naught. Let me pause here for 5 seconds and show you a point of confusion that happens sometimes. Oftentimes people confuse between what is called the element, the variable associated with the element versus the element value. Okay, notice that here, capital V naught is the voltage that this voltage source provides, while this name here, V naught, is simply a variable that we've used to label the voltage across that element. So similarly, I can label V1 as the voltage across the resistor, and I1 as the current flowing through the resistor. So this method of labeling, where I follow the convention that the current flows into the positive terminal, is called the associated variables discipline. I will try to use the word discipline in situations where you have a choice, okay? And of a variety of possible choices, you pick one as a convention, okay? So here, as a convention, we use the associated variables discipline and use that method to consistently label the unknown voltages and currents in our circuits. Okay, so let me continue the labeling here. V4, I4, I3, V3 here, and V2 and I2, V5 and I5. I think that's it. So I've gone ahead and labeled all my unknowns. So each of these voltages and currents are the voltages and currents associated with each of the elements, and my goal is to solve for these. Okay? So in terms of our solution here, let's follow the method that I outlined for you. So as a first step, I'm simply going to go ahead and write down all the element VI relationships. Okay, so as a first step, I'm going to go ahead and write down all the VI relationships. So can someone yell out for me the VI relationship for the voltage source? Okay, good. So V0 is capital V0. That is that the variable V0 is simply equal to the voltage V0. Similarly, I can write the others. V1 is I1 R1. V2 is I2 R2, and so on. Okay? And I have 1, 2, 3, 4, 5, 6 elements, so I will get 6 such equations. Step 2, I'm going to go ahead and write KCL. KCL for the nodes in my system. And so let me start with node A. So for node A, I get, let me take as positive the currents going out of the node. So I get I0 flowing out plus I1 flowing out plus I4 flowing out, and they must sum to 0. Okay, for node A. Then I can go ahead and do the other nodes. Let's say, for example, I do node B. For node B, I have I2 going out, that's positive, I3, and I1 is coming in, so I get minus I1 equals 0. Okay, so I have 1, 2, 3, 4. I have 4 nodes. Okay, so I would get 4 equations. Okay, it turns out that the 4th equation is not independent. You can derive it from the others. So I get 3 independent equations out of this. I can then write KVL. And for KVL, I just go around my loops here. And let me go through the this first loop here in this manner. Okay, and a simple trick that I use, you have to be incredibly careful when you go through this in keeping your minuses and pluses correct. Okay, otherwise you can get hopelessly muddled. Once you label it, okay, you need to be sure that you get all your minuses and pluses correct. So for KVL, what I'd like to do is, let's say I start at C. Okay, let's say I start at C, and from C I'm going to go to A, from A I'm going to B, and from B I'm going to come back to C. Okay, that's how I traverse my loop. And the trick that I'm going to follow is, as my finger walks through that loop, I'm going to label the voltage as the first sign that I see for that voltage. Okay, so when I start from C and I go up, I start by punching into the element, the voltage source element, and then punch into it, I hit the minus sign for the V0. Okay, so I'm just going to write down minus V0 plus. Then I go through, and as I come up to A and go down to B, I punch to the plus sign of the V1. So that's plus V1. And then I punch into the plus sign of the V2, and so I get plus V2, and that is 0. Okay? Good. So that matches what you have in your notes as well. So this is the first equation. Similarly, I can go through my other loops and write down the equations for each of the loops. Okay? And a convention that I like to follow is, as I go through the loop, I write down as a sign for the voltage the first sign that I encounter for that element. Okay? You can do the exact opposite if you want just to be different. But, you know, as long as you stay consistent, you will be okay. All right. So in the same manner here, there are 4 loops that I can have, so 4 equations. Again, one of them turns out to be dependent on the others, so I end up getting 3 independent equations. So I get a total of 12 equations. There are 12 equations. There are 6 elements. Okay, voltage source and 5 resistors. So there are 6 unknown voltages and 6 unknown currents. Phew. So I have 12 equations and 12 unknowns. Okay, I can take all these equations and put them through a big crank and sit there and grind. And if I was really cruel, I'd give this as a homework problem and have you grind and grind and grind till you get your 6 voltages and 6 currents. Okay, it works. Okay, so you get 12 equations, and this method just works. However, notice that this is quite a grubby method. It's quite grungy. You know, I get 12 equations, and it's quite a pain, even for a simple circuit like this. However, suffice it to say that this fundamental method that is just one step away from Maxwell's equations simply works. Okay? So what we'll do is, in the rest of this lecture, I'll introduce you to a couple more methods. One is an intuitive method, and another one called the node method is a little bit more formal, but is much more, I guess, much more terse than the KVL, KCL method. Method 2. So the relevant section to read in the course notes is section 2.4. One of the things that I will be stressing this semester is intuition. Okay, what you will find that as you become EECS majors and so on and go on, or if you talk to your TAs or your professors and so on, you will find that very rarely do they actually go ahead and apply the formal methods of analysis. Okay, by and large, engineers are able to look at a circuit and simply by observation write down an answer. And usually in the past, what we've tried to do is kind of ignored that process and told our students that, look, we'll teach you all the formal methods and you will, develop your own intuition and be able to do it. What I'm going to try to do this term is try to stress the intuitive methods and try to show you how the intuitive process goes so you can very quickly solve many of these circuits simply by inspection. Okay? So this method that I'm going to show you here is one such intuitive method, and call it the element combination rules. Okay, for many simple circuits, you can solve them very quickly by applying this method. The components of this method are these. I learned about how to compose a bunch of elements. So let's say, for example, I have a set of resistors, R1 through Rn, in series. Okay? You can use KVL and KCL to show that this is equivalent to a single resistor whose value is given by the sum of the resistances. Okay? So if I have resistances in series, then effectively it's the same as if there was a single resistor whose value is the sum of all the resistances. Okay? You can look at the course notes for a proof of, for a derivation of this fact. Similarly, if I have resistances in parallel, so let me call them conductances. Conductance is the reciprocal of a resistance. If resistances are measured in ohms, conductances are measured in mhos, MHOs. Okay? So let's say the conductances are G1, G2, and G3. Then effectively, this is the same as having a single conductance whose effective value is given by the sum of the conductances. Okay? Conductances in parallel add, and resistances in series add. Similarly, for voltage sources, if I have voltage sources in series, then they are tantamount to the sum of the voltages. And similarly, for currents, if I have currents in parallel, then they can be viewed as a single current source whose currents are the sum of the individual parallel currents. So let's do a quick example. So let's do this example. So let's say I have a circuit that looks like this, and 3 resistances. And let's say all I care about is the current I that flows through this wire. All I care about is that current. Of course, you can go ahead and write KVL and KCL. You will get 4 equations, and there are 4 unknowns, and you can solve it. But I can apply my element combination rules and very quickly figure out what the current I is using the following technique. So what I can do is I can first of all take this circuit, and I can compose these 2 resistances and show that this circuit is equivalent, as far as this current I is concerned, to the following circuit, R1, and I take the sum of the 2 conductances, okay, and that comes out to be R1, R2, R3, R2 plus R3, and then I can further simplify it, and I get a single resistance whose value is given by R1 plus R2, R3, R3. Okay, I'm just simplifying the circuit. Now, from this circuit, I can get the answer that I need. I is simply the voltage V divided by R1 plus Okay? So in situations like this, where I'm looking for a single current, I can very quickly get to the answer by applying some of these element combination rules, and I can get rid of having to go through a set of formal steps. So in general, whenever you encounter a circuit, by and large, attempt to use intuitive methods to try to solve it, and go to a formal method only if some intuitive method fails. Even in your homeworks, by and large, the homeworks are not meant to be grungy. Okay, if you find a lot of grunge in your homework, just remember, you are probably not using some intuitive method. Okay, so just be cautious. All right. So let me go on to the third method of circuit analysis, and the third method is called the node method. So the node method is simply a specific application of the KVL-KCL method and results in a much, much more compact form of the final equations. If there's one method that you have to remember for life, then I would say just remember this method. Okay, the node method is the workhorse of the EECS industry. Okay, if there's one method that you want to consistently apply, then this is the one to remember. So let me quickly outline for you the method and then work out an example for you. The first step of the node method will be to select a reference or a ground node. This is a symbol for a ground node. The ground node simply says that I'm going to denote voltages at that point to be 0 and measure all my other voltages with reference to that point. So I'm going to select a ground node in my circuit. Second, I'm going to label the remaining voltages with respect to that ground node. So label voltages for all the other nodes with respect to the ground node. Next, write KCL for each of the nodes, write KCL. Okay? Don't write KCL for the ground node. Remember, if you have n nodes, the node equations will give you n minus 1 independent equations. So write KCL for the nodes, but don't do so for the ground node. Then, solve for the node voltages. So let's say when we label voltages, I'm going to be labeling them as E something or the other. So solve for the unknown node voltages. And then, once I know all the voltages associated with the nodes, I can then back solve for all the branch voltages and currents. Okay, once I know all the node voltages, I can then go ahead and figure out all the branch voltages and the branch currents. So let's go ahead and apply this method and work out an example. Again, remember, if there's one method that you should remember, it's the node method. Okay? And when in doubt, consistently apply the node method and it will work. Whether the circuit's linear, non-linear, you know, whether the resistors are built in the US or USSR, doesn't matter. Okay? The node method will simply work, linear or non-linear. Okay? So what I'm going to do is I'm going to build a circuit that's my old faithful. It's our old faithful. Plus, I'll make it a little bit more complicated by adding in a current source. So let's go have some fun. Let's do this. So here's my voltage source as before. Okay. What I'll do is, for fun, add a current source out there, and you can convince yourselves that if you go and apply to the KVL, KCL method, it'll really be a mess of equations. Okay, so R1, R3, R4, R2, R5. Okay, so let's follow our method and just plug and chug here. So let's apply the first step. I select a ground node. It's a reference node from which I'll measure all my other voltages. Okay? Now, without knowing anything about the node method, try to use your intuition as to which node you should choose as a ground node. Okay, remember, you want to label the ground node with the voltage 0 and measure all the other voltages with respect to that node. Okay, and a usual trick is to pick a node which has the largest number of elements connected to it as the ground node. Okay? And in particular, you will find out later, it's useful to pick a node to which all your voltage sources, the maximum number of your voltage sources are also connected. Okay, so in this instance, I'm going to choose this as my ground node. Okay, that's my first step. I chose that as my ground node, and I'm going to label that as having a voltage 0. Second step, I'll label the voltages of the other branches with respect to the ground node. Okay, so what I'll do is have this node here. So I'm going to label that voltage E1. These are my unknowns. Remember, node method, because my node voltages are my unknowns. So I label this as E1. I label this one as my unknown voltage E2. What about this one here? Is that voltage unknown? No, I know what the voltage is because I know that this node is at a voltage V0 higher than the ground node. Okay? Notice that to go from here to here, I directly go through a voltage source, and so this node has voltage V0, and I'll simply write down V0. Okay? If you try to simplify the number of steps that you have to go through, so directly go ahead and write down the voltage V0 for that node. What I will also do is, for convenience, I am going to write down, I'm going to use conductances. So I'm going to use GI in place of 1 by Ri and write down a bunch of node equations. Okay, so step 1, I've chosen my ground node. Step 2, I've labeled my node voltages E. Okay, I've done with 2 of my steps. Now let me go ahead and okay, so let me go ahead and apply step 3. And step 3 says, go ahead and apply KCL for each of the nodes at which you have an unknown node voltage. And then that will give you your equations. So let me start by applying KCL at E1. So let me write KCL at E1. I do one more thing. Notice I don't have any currents there. Okay? So how do I write KCL? KCL simply says the sum of currents into a node is 0. Again, remember, by the lumped matter discipline. So the currents, but I don't have currents in there. So the trick that I adopt is that to write KCL, I use the node voltages and implicitly substitute for the node voltages, divide by the elemental resistance, for instance. So take the node voltages and divide by the resistance, get the current. Okay, so I implicitly apply element relationships to get the node currents. So the example will make it clear. So I take node E1, and again, currents going out, I'm going to assume to have be positive. So the current going up is E1 minus V0 divided by R1. So multiplied by G1. That's the current going up, plus the current going down is E1 minus 0. The ground node potential is 0. G2. Okay, plus the current that is going through resistor R3, which is simply E1 minus E2 divided by R3. So E1 minus E2 divided by R3, or multiplied by G3, is equal to 0. Okay, see how I got this? This is simply KCL, but to get my currents, I simply take the differences of voltages across elements and divide by the elemental resistance, and I get the currents. Okay, so I can similarly write KCL at E2. So at KCL at E2, again, let me go outwards. So the current going up is E2 minus V0 multiplied by G4. The current going left is E2 minus E1 divided by R3, or multiplied by G3. The current going down is E2 minus 0 multiplied by G5. And the current going down is minus I1. Okay, you've got to be careful with your polarities here. So all the currents going out sum to 0. And so here are the currents that are going out at this point. So what I do next is I can move the constant terms to the left-hand side and collect my unknowns. So let me write them out here. So let's say I get E1 here, okay? And so from this equation, I have a V0 G1, which comes out here. So minus V0 G1 comes over to the other side. And let me collect all the values that multiply E1. So I get G1 is one example. I have G2, and I have G3. And then for E2, I have minus G3. Okay? So I've simply expressed this as the element voltages multiplied by some terms in parentheses, and I put my external sources on the right-hand side. Similarly, I go ahead and do the same thing here. In this instance, let me move my sources to the right. So I get I1 coming out there, and I get V0 G4 coming out there. By the way, I just want to mention to you that if you're looking to fall asleep, this is a good time to do so, because as soon as I write down these two equations, okay, from now on it's a nap time. There's nothing new that you're going to learn from here on. Okay, it's just Anand Agarwal having fun at the blackboard, pushing symbols around. So once you write down these two node equations, the rest of it is just grubby math. So let me just have some fun. So let me go ahead and do that. So I move my voltages and currents to the other side, and let me collect all the coefficients for E1 here. So E1 is minus G3, and that's it, I guess. Okay. And then I do the same for E2. So I get G4, and I get G3, and I get G5. Okay? So notice here that I have two equations, and two unknowns. Okay, the two equations are, on the right-hand side, I have some voltages and currents, which are my drive voltages and drive currents. Okay, so actually, this is getting quite boring. So I'm going to pause here and talk about something else. So you can take this and you can put this in matrix form. So I've done that for you on page 10. You can say, oh, matrix form, yeah, I know that. You can use any technique to solve it. Use algebraic techniques. Use linear algebraic methods to solve it. Use a computer, whatever you want. And computers. When computers analyze circuits, they write down these equations and deal with solving matrices. So when you took a linear algebra class, how many people here have taken a linear algebra class? How many people here have heard of Gaussian elimination? And how could more people have heard of Gaussian elimination than took a linear algebra class? But anyway, so now you know. So now you know why you learned about why you took those linear algebra classes. And so if I just collected these into matrix form, okay, so I just simply express those two equations in linear algebraic form. And here's my column vector of unknowns. And you can apply any of the techniques you've learned in linear algebra to solve for this. Gaussian elimination works. Okay? And in people doing research in computer techniques for solving such equations simply deal with huge equations like this. Building computer programs that, given equations like this, can go ahead and solve them. Okay? So let me stop here and re-emphasize that what we've done is made a huge leap from Maxwell's equations to using the lumped matter discipline to KVL and KCL, which ended up giving us simple algebraic equations to solve and not having to worry about partial differential equations that were the form of Maxwell's equations.